Good afternoon, everybody. Today we are going to explain the second part of chapter number 11, which is the heat exchanger device. Based on the previous example, we have explained the heat exchanger and how was the usage of the cross flow. So today we are going to complete with two examples. The first example is mentioning that consider the heat exchanger design is same as the previous example. That is fin tube cross flow heat exchanger with a gas side overall heat transfer coefficient is providing as 100 and the area is providing as 40. The water flow rate and the inlet temperature is remaining as 1 kilogram per second and the temperature inlet is equal to 35. However, a change in operating condition for a hot gas generator causes the gas to now enter to the heat exchanger with the flow rate is equals 1.5 kilogram per second and the temperature is equals to 150. So now from the question we can figure out that the question providing for us two mass flow rate and at the same time providing for us two inlet temperature, one for the cold, one for the hot. So the question also providing for us the area and the overall heat transfer coefficient. So from these kind of the data that we can able to calculate the heat maximum by finding the heat maximum by finding the C minimum from the cold and the hot, and we are able to use the table by using only the inlet temperature. Please don't assume anything. So according to this one, we'll be able to go to the table by finding the CP for the cold and the CP for the hot, and then we will be able to find which one is the C minimum. After finding the C minimum, we will be able to find the heat rate and for the working fluid, and sorry, the maximum. Then we will be able to calculate the rest of the information. So based on the question here, the question has provided for us two heat inlet, two mass flow rate. Then the question looking for the differential of the temperature. So back to the question, what is the rate of heat transfer by the exchanger? So the question looking for the heat rate of the working fluid. And what are the gas and water outlet temperature? So both outlet temperature is not providing in the question. So according to this one, we'll be able to find the C cold and C hot based on the data providing. Then we'll be able to find the C minimum. From the C minimum, we'll be able to find the capacity ratio. From the capacity ratio, we'll be able to go to the tables or to the chart. Based on the solution, we'll be able to find the NTU by finding the overall heat transfer coefficient and the area from the question, and C minimum based on the calculation we found it as C hot. But from this, we'll be able to calculate the Q maximum because it's depending on the both inlet temperatures. Then based on the effectiveness from the table, we'll be able to find the heat rate, which is equals 0.82 from the effectiveness from the equation. Then we'll be able to find the heat maximum based on the calculation we found it earlier. So we'll be able to find the heat rate of the working fluid. From the heat rate of the working fluid, we'll be able to find the T hot and the T cold. Then up to here, the question has been done. The other question, which is the last question of the chapter, is mentioning the condenser of a large steam power plant is a heat exchanger in which steam is condensed to a liquid water. Assume the condenser to be shell and a tube. Is different from the previous example. The previous example we have cross flow, now we have shell and a tube. So based on the solution, the NTU calculation and the effectiveness, it will be from different formula or different charts depending on your easier way to solve. So we have shell and tube heat exchanger consisting of single shell and 30,000 of tubes. So we have single shell and 30,000 of tubes. It looks like the condenser in the big system of the HVAC. Each executing two passes, which is inlet and the outlet. So according to this one, the tube are thin walled construction with the diameter is equals 25 millimeter. Please don't forget to convert it to meter. And steam condense on their outer surface with an associated convection coefficient, which is equals 11,000. So as I mentioned earlier many times, don't let the question cheat you. Once the question provides for you H out, means the question is looking for H in to be able to calculate the overall heat transfer coefficient. So the heat transfer rate that must be affected by the exchanger is equals 2 billion watt, and is accomplished by passing cooling water through the tubes, which equals 3 multiplied by 10 power 4, which is 30,000 again. So in this case, each tube will be able to carry 1 kilogram per second. The water enters at 20 Celsius, while the steam condenses at 50. So the question here mentioned clearly for us that, well, the steam condenses at 50, means we have fixed temperature for the hot pipe. So according to this one, we can figure out that the C hot, it could be considered infinity. While if the C hot is infinity, is clearly that we can find that the cold section is the C minimum. And according to this one, the capacity ratio, it will be considered 0. This one will help us to calculate the effectiveness and the NTU from the chart or from the equations. Now, the question is looking for what is the temperature of the cooling water emerging from the condenser. At the same time, looking the required tube length per pass. So the first one, the question looking for the temperature of the cooling section, because as we have mentioned earlier that we don't have anything for the hot section, and the L we will be able to calculate it from the area, which is the NTU is equals overall heat transfer coefficient multiplied by area over the C minimum. So according to this one, we will start to solve the question. So first, better to draw for yourself how it looks like the design of the question. We have shell and we have tube, which is inner and outer passing through the shell. And this is the diagram that will help us to understand how the flow is going on. So from the data they're providing, we will be able to find from the temperature inlet only, don't assume please in the exam. So from temperature inlet, we will be able to find the CP to be able to calculate the rest of the data. So according to this one, the heat is providing, temperature inlet is providing, mass flow is providing, so we'll be able to calculate the CP from the chart, from the table. Then we'll be able to calculate the T temperature called out from the normal equation, which is MCP delta T. By finding this, as I mentioned earlier, don't let the question cheat you by providing the H out. So in this case, we will be able to calculate the H in. So we need to go back to chapter number 3 to find this equation. And we need to go back again to chapter number 8 to be applied as internal flow inside the pipe. So the Reynolds number is equals 4 m dot over pi d mu. So according to the question provides for us m dot and provide for us the diameter. So in this case, we need to go to the table by finding from the temperature inlet of the cold section to calculate the mu only. So based on this, we will be able to calculate the Reynolds number. If the Reynolds number is more than 4,000, it's considered turbulent. So based on the turbulent, we have equation for the Nusselt number that is equals 0.023 Reynolds number 4 over 5, then Brighton number 0.4. So from this kind of the equation, we will be able to find the Nusselt number. From the Nusselt number, we'll be able to calculate the H in. So then we'll go again to the overall heat transfer coefficient to be calculated. So from this, as I mentioned earlier, the C hot is infinity and the capacity ratio is equals to 0. So by clear that we can able to find the C minimum, it is for the cold section. So the working fluid is cold. So according to this one, the heat maximum that is to be calculated by the both inlet temperature, which is provided in the question, then we'll be able to calculate the effectiveness, while the heat is provided in the question, and the Q maximum we have already calculated. By finding the effectiveness, we will be able to calculate the NTU from the chart. Then from this part, we will be able to solve the question by finding L from the area based on the question provided. I wish you best of luck for your test 2 and the final exam. Good luck. Thank you very much.